Welcome to our presentation on disentangling racial phenotypes, fine-grained control of race-related facial phenotype characteristic. Today I will talk about our novel approach to achieving fine-grained control over race-related facial features. In computer vision, addressing racial bias typically involves ensuring that performance metrics are similar across different racial groups. This is known as group fairness. However, this raises important questions. Which racial groups should be included in these assessments? What defines racial categories? Previously, we proposed analyzing racial bias by focusing on specific facial phenotype attributes, providing a more nuanced approach compared to the traditional methods. Additionally, disentanglement learning has shown promise in enhancing group fairness by isolating individual attributes. Accordingly, in this study, we ask, can we effectively disentangle racial phenotypes and generate various combinations for any given face? Our work aims to address this by proposing a framework that allows for precise control and manipulation of racial phenotypes. In this study, our contributions are a framework that achieves explicit control over identity-relevant race-related facial phenotypes via single factorized and disentangled latent space. And our framework only relies on simple handcrafted 2D matrix parameter obtained by public face datasets. We also introduced a Celeb HQ augmented clean dataset, which is the first semi-synthesized, manually cleaned, diverse and high-quality dataset for generative models. In our approach, we utilize a factorized latent space to represent race-related facial phenotypes. By decomposing the latent space into distinct factors, we can isolate and manipulate specific facial attributes such as skin tone, hair color, facial feature shapes independently. We use a combination of color histograms and segmentation algorithm to accurately extract skin and hair color from images. We employ landmark detection to identify and isolate specific facial features such as nose, eyes, and mouth. Each feature is represented as a separate factor within the latent space, allowing for independent manipulation. This allows for fine-grained control over these phenotypes, enabling us to generate diverse and realistic facial images with precise racial characteristics. Our framework, shown in the figure, contains multiple shared generators and discriminators. Skin tone, hair color, facial feature shapes are introduced via the concatenated vector ZC from separated encoder outputs. A domain discriminator ensures encoder F generates similarly factorized mapping vectors of the input images to ZC. The StyleGAN2 architecture maps the vectors to regenerate high-quality images. We propose a semi-augmented dataset including 26,000 high-quality and diverse images to provide a better training and evaluation. We augment these images from Celeb HQ using our previous work based on image-to-image translation. In inference, we don't have to get the metrics to the parameter metrics for the facial phenotypes, as we only use encoder F and generator. encoder F will provide the factorized mapping for the image, and then the manipulation on the factorized latent space will enable us to generate differentiating images. We show our results on controllability and photorealism. For the controllability, we trained the attribute classifier to identify generated images attributes. Comparing to the previous work, ConfigNet, the baseline work, we achieve higher control for the hair color. For the rest of the attributes, we cannot compare with the baseline as they didn't have these attributes. But for the skin types, we can see that the positive mean prediction for the intended generated images is higher. For the image quality evaluation, we achieve lower FID score, meaning that higher image quality comparing to the baseline config network without using any 3D data. Our generated image results. Accurately disentangling shape-related facial features remain challenging comparing to the hair and skin color attributes. And our framework struggles with specific phenotype combinations, and unintended entanglement can occur during inference due to the training distributions of the training sets. Thank you for listening.